Welcome. In this video, we are going to have a look at a machine learning interview question. It's a question from my ebook. I will put the link in the description if you want to go further. But this question is about adversarial attack. It's okay if you don't know what adversarial attack. It's okay if during the interview you are asked this question and you don't know what it is. Because the first part of the question is a bit theoretical. It's just to assess your machine learning culture, to see if you know what it is. But even if you don't know what it is, the interviewer will explain to you what it is. But then once you are given this information, you should be able to answer the second part of the question. So given what the interviewer tell you about adversarial attack, you should be able to derive the loss function. Okay? So basically, what is your adversarial attack? And again, if you know what it is, it's really great. It shows that you have some machine learning culture. If you don't know, that's not an issue. Or at least if I was the interviewer, what's really important for me, really the interview starts after that, okay? If you know that, that's bonus. That shows you have some culture. But what's really important is what's following up. Or from that, you are able to derive the loss function. Okay, so it's an adversarial attack. The idea is to add a very small perturbation to the image. So basically, we add a perturbation delta, very small, so smaller than some constant epsilon, such that it maximizes the model loss. So for example, if we are doing classification, we maximize the loss. So okay, what does that mean intuitively? So for example, let's say you have a neural network that classify faces, for example. Let's say that's a facial recognition. But what you want to do, you want to attack this neural network that does facial recognition. So Y is a label. So you want the neural network to misclassify a person, for example, to answer a system without having the proper, the proper face. Let's put it that way. So basically, here you have an image X. You add very small noise to the image X, so that the image looks almost the same. Or from a naked eye, you cannot see that there was some noise added to it because it's very small noise. But the neural network is completely lost on makes a misclassification. Okay, because you have optimized this noise very carefully so that it maximizes the loss. Okay, and because neural networks by default are not Lipschitz, so basically Lipschitz function is a function that if you add a very small perturbation to it, the output will vary very slightly. Here, with neural networks, you can have a neural network where you add a very small amount of noise, but the output of the neural network is very different. You have a big difference in the output, okay? And that's why you can do adversarial attack. So, of course, a way to defend from adversarial attack is to have a Lipschitz, to have a neural network that is Lipschitz, but it's not easy to do. But we are going to treat that in other videos, okay? So once this is said, you should be able to derive the loss function. On here, now that the interview starts. Okay, so you can pause this video, try to derive the maths, or to derive the loss function. But yeah, let's move on. So basically here, as we've said, we want to maximize the loss. So usually you do some training to minimize the loss. Here we want to do the opposite. We want the neural network to misclassify the label Y. So we want to maximize the loss on Y instead of minimizing it, okay? The input to the neural network is not X, it's X plus delta. So X plus delta is our new input, but we want this new input to be very close to X. We want to add some noise so that humans do not see that we have done an attack. For humans or for automatic systems, they should not be able to see that there was an attack, okay? So with a constraint, we want that delta, the noise that we had, we want it to be very small. So for example, we want its norm to be smaller or equal to epsilon, okay? So it's really an optimization problem. We used to do that in machine learning. So for example, you can for example solve it with a projected gradient descent. So the loss is the cross entropy loss. So basically, you want to minimize f of theta of x prime. So x prime is our new input, so x plus delta. You want x plus delta to be close to x. So basically you want x prime minus x to be smaller or equal to epsilon. So basically that's the same as saying delta smaller or equal than epsilon. So there are two ways to solve that. Either your loss is the cross entropy loss of x prime, on one side you have the cross entropy loss, on the other side, right, you want x prime to be close to x. So basically you can add an extra term in your loss where you minimize the mean squared error between x prime and x. So that's one way to do it. Or the other way to do it is explained here with projected gradient descent. Okay, so that's the first way to do it. So basically you just have this loss. You want to maximize this cross entropy loss, but you also want to have delta smaller or equal than epsilon. So either you do projected gradient descent to make sure that x prime stays close to x, or you just add an extra term in your loss to constrain x prime to stay close to x. Maybe I can make a video where we go deeper, where we do the implementation from scratch in PyTorch. If you're interested, let me know in the comments. I will only do it if there is interest and if enough people ask for it. Okay, so that's the first way to do it, optimization-based attack. And now we'll see another way to do it that is in a way smarter, and that's really the difference between a machine learning engineer that is a salary of 100k per year, for example, on a machine learning engineer that is a salary of 2 million per year. Okay, there are very good machine learning engineers that have crazy signing bonus. It ranges from 1 million to 100 million just for the signing bonus nowadays. On here, that's really what makes the difference between a very good machine learning engineer on a decent machine learning engineer. On that can have big consequence, both for the engineer, its salary, but also for his company, on its impact in the company. The issue with this first approach, optimization-based attack, is that you need to solve an optimization problem, right? So every time you want to do an attack, you need to solve, for example, you need to do projected gradient descent, so you need to do gradient descent. So you need to burn some compute, okay? But what you can do, you can use this this approach as usual with the questions from my ebook that I reference. So for example, you can have a look at the papers that introduce those methods. But here the idea is to say, okay, this parameter delta, this noise delta is very small. So what I can do linearization around x using a first order Taylor expansion, and I can rewrite my term, so basically my loss, like this. So basically I'm just applying a Taylor expansion, and we want to know we know we want to maximize this term, so the term on the leftmost side. On the rightmost side, the first term, it's not a function of delta, so we can for now we can put it aside. So basically what we want to do, we want to maximize the term on the left, so we want to maximize the term on the right. We know that the first term is not a function of delta, so we don't care about it. So what we really want to do is to maximize the term, this term, the gradient of x with respect to the loss function, transpose multiplied by delta. Basically we want to that reduce our optimization problem to a simple linear program. Okay, so we want to maximize this, or we want to find delta that maximize this, and there is a closed form solution for that. So basically if we solve it, we find this equation for delta star, so basically delta that maximizes this term. On this is basically that's a simple equation that you can implement directly. So basically that means that for a given image x, if I have manually talked f of theta, so I want to find delta that will make this manually talk misclassify some image. So we'll make sure that x is labeled y, or that x misclassify y. It depends how we phrase the attack. Then I can compute delta directly, okay? And therefore I don't need to solve any optimization. I can just plug delta into my my attack. So I just say x hat is equal to x plus delta star, I would invite you to have a look at those papers. It's really impressive. You have an image, the image X. You have the image X hat. It really looks like X because delta is very small, but the neural network give very different classes to X and to X hat. So here we assume that we have access to f of theta, that we can compute its gradient with respect to X. So we call that an open box attack because we have access to f onto its gradient, but there are also black box attack when you don't have access to the neural network, you don't have access to its weights. So for example, ChatGPT, you don't have access to the weights of ChatGPT, but there are still ways to do attack without having access to the weights. We might cover that in other videos. So I really hope you like this video. If it was, leave the thumbs up, comment, just to give a reach to this channel, to help it to get discovered, and subscribe for more content related to that. Thank you.